Welcome to the deep dive. Today we are leaving behind the theoretical comfort of ideal gases, where atoms just perfectly ignore each other.
Yeah,
And we're jumping into the much messier, much more interesting reality of condensed phases.
exactly. I mean, when you're talking about liquids and solids, interaction isn't just some background noise. It is everything. It's the main event. We're getting into the world where interatomic forces, things like bond energies, atomic size, they dictate the entire game.
They dictate thermodynamic stability, solubility, how materials actually behave in the real world.
Yeah.
So we're really laying the foundation for a huge chunk of material science here. Our job today isn't just to, list off equations. It's to get at the physical meaning behind them. What are the key things we need to pull from this dive into solution thermodynamics?
Our mission really is to boil this down to the crucial concepts. We'll start with the most basic definitions and then build up through the laws, the derivations. The goal is for you to be able to physically interpret what's going on. What does a positive deviation actually mean for the atoms? How does activity work?
And how does all of that connect to predicting whether a material will hold together or just, well, fall apart into different phases?
Right. This is your key to really understanding phase diagrams.
Okay, let's start at the absolute baseline then. The concept that anchors almost all of the experimental data here. The saturated vapor pressure of a pure liquid, let's call it A or PPA, this is the pressure you get when the liquid and its vapor are in dynamic equilibrium.
And the key insight here isn't just that it's an equilibrium, it's about what controls the rate of evaporation. For an atom to, escape the liquid surface, it needs a kick. It has to overcome the attractive forces of its neighbors.
It needs a certain activation energy.
Exactly, and that energy is determined by the bond strengths, by how deep that potential energy well is for the surface atoms. So the vapor pressure is super sensitive to temperature, but also to how strongly those atoms are holding on to each other.
Okay, so now let's add a second component, B, into the mix. The most idealized, simplest situation is described by Raoult's law. PD body equals X butter times P bar. The partial pressure is just its mole fraction times the pure vapor pressure.
It's beautiful in its simplicity, but you have to remember the massive assumption it makes for it to work across all compositions.
The solution has to be completely random.
Completely random, which means the AAA, BB, and AB bond energies have to be identical. If they are, the atoms don't care who their neighbors are, and the solution can achieve maximum configurational entropy. That's what makes it ideal.
But of course, most real systems are anything but ideal. And that non-ideality, especially in dilute solutions, is where Henry's law comes in. PP equals some constant, K Bellers times X people. So why does the pressure of B suddenly stop following that ideal Raoult's line?
Well, this is where the physics really pops. Henry's law is what happens when that solute atom, B, finds itself totally surrounded by solvent atoms, A. If that AB interaction is different from the AA or BB interactions, the whole energy landscape for B changes.
So what are the consequences of that change?
Let's imagine the A and B atoms are really attracted to each other. The AB bond is way stronger than the others. That B atom is now sitting in a much deeper energy well. It's a lot harder for it to escape.
It's sticky.
It's sticky, exactly. And because it's sticky, its evaporation rate plummets. That is a negative deviation. The actual vapor pressure is lower than Raoult's law would predict, so the Henry's law line sits below the ideal line. This suggests the atoms actually want to order themselves. They prefer mixed neighbors.
Like in the iron-nickel system.
Just like liquid iron and nickel. And the opposite.
When they don't like each other.
Right. That's a positive deviation. If the AB bond is weak, the B atom is in a really shallow well, so it's much easier for it to escape. It's more volatile than you'd expect. The vapor pressure is higher, and the Henry's law line lies above the Raoult's line.
And that suggests the atoms would rather cluster with their own kind.
It does. It points towards phase separation. The atoms prefer their own neighbors, which is why something like liquid iron and copper don't really want to mix.
Okay, let's formalize this. To really get into the thermodynamics, we need to talk about activity. It's sort of the effective concentration of a component, right? It accounts for all those non-ideal interactions we just talked about.
That's a perfect way to think about it. Formally, for some component, its activity is just its partial pressure, pi lus divided by the pressure of the pure component. So A equals pi lus over pi.
It's a ratio, so it's unitless.
Unitless, and this is critical, in any stable solution at equilibrium, activity can never be more than 1. It's always a measure of how available that component is compared to when it's pure.
And to quantify how non-ideal a solution is, we use the activity coefficient, which is gamma. the gamma. That's just the activity divided by the mole fraction. Gamma I usually are deal.
Mm-hmm. And this is our little window into the thermal behavior. If gamma equals 1, it's ideal. If it's more than 1, positive deviation. Less than 1, negative.
And there's a direct link between gamma and temperature.
There is through the Gibbs-Helmholtz relationship. We don't need to walk through the whole derivation, but the final result is so important. It shows that how gamma changes with temperature is directly proportional to the partial molar enthalpy of mixing, delta hema.
So what does that tell us?
It tells us that temperature is the great equalizer. I mean, if you have a positive deviation, so gamma is greater than 1 mixing is endothermic, it absorbs heat. So if you crank up the temperature, you're helping it along, pushing gamma down towards 1.
And if it's a negative deviation?
The opposite. Mixing is exothermic. It releases heat. So increasing the temperature actually works against it and pushes gamma up toward 1. In almost every case, a higher temperature drives a non-ideal solution closer to ideal Raoultian behavior.
Now, this is where it gets really useful for anyone in a lab. You might only be able to measure the activity of one component, maybe the one that's more volatile. You need a way to figure out the other one, and that's the Gibbs-Duhem relationship.
Yes. The Gibbs-Duhem equation is, it's basically a statement of thermodynamic consistency. It says that for any little change in composition at constant P and P, the changes in the partial molar properties have to balance out.
They're intrinsically linked.
They are. For a binary system, it's basically sex dollars times the change in property A plus x dollar times the change in property B has to equal 0. So if you know the activity of B across the whole composition range, you can integrate that, and you must be able to find the activity of A.
It's a mathematical requirement. And this leads to a really powerful conclusion, one that links the two laws we've just discussed.
It really does. The Gibbs-Duhem equation proves that in any composition range where the solute, B, is obeying Henry's law, the solvent, A, absolutely must be obeying Raoult's law.
That's incredible. So they're not two separate ideas. They're two sides of the same thermodynamic coin, forced to behave in a consistent way.
Exactly. And you see this in real systems. In the liquid iron nickel system, nickel follows Henry's law up to about 30%. And in that entire range, the iron solvent is perfectly Raoultian. It has to be.
All right, let's zoom out from the partial properties to the whole system. Let's talk about the integral Gibbs free energy of mixing, delta GM. For 1 mole solution, it's just the weighted sum of the partials. Delta GM is XA delta GM plus XB delta GME away.
And if we write that in terms of activity, which is more useful, we get delta GM equals RT, XALNAA plus XBNNAB. Plotting that function of delta GM versus composition gives you the curve that tells you everything about stability.
Okay, and from that curve, you can use a graphical trick called the method of tangential intercepts. Since we don't have a figure in front of us, can you just sort of paint a picture of how that works?
Sure. Imagine you have this downward curving bowl shape for the delta GMY curve. If you pick any composition, say 50-50, and you lay a ruler down so it's perfectly tangent to the curve at that point.
Okay.
The points where that ruler, that tangent line, hits the pure A axis on the left and the pure B axis on the right, those intercept values are exactly the partial molar Gibbs free energies of A and B at that specific 50-50 composition. It's a brilliant visual tool.
It tells you the driving force for adding just one more atom of A or B.
That's exactly what it is.
Okay, so to really understand what's going on with non-ideal solutions, we have to have the ideal solution baseline memorized. Let's just quickly run through those properties where activity equals mole fraction.
Right, the baseline. 3 key things.
First, there's no volume change on mixing. Delta Vm then is 0. In solids, this leads to things like Vgard's law, where lattice parameters are linear. Second, the enthalpy of mixing, delta HM is also 0. No heat is released or absorbed.
And third, the entropy of mixing, delta SMide, is purely combinatorial. It's described by that famous equation XA ln XA plus XBA ln XB, and that function is always positive. It's the randomness you gain by mixing.
So if there's no enthalpy change, what's actually driving an ideal solution to form?
It's pure entropy. That's it. The Gibbs free energy is just delta JMI -D9. And since entropy of mixing is always positive and temperature is positive, the Gibbs free energy of mixing is always negative. Ideal solutions will always want to mix. Entropy is this relentless force pulling them together.
Okay, with that baseline, let's introduce the simplest model for non-ideal behavior that actually lets us predict phase separation, the regular solution model.
Yes. This is a brilliant step. We keep the entropy ideal, we still assume maximum randomness, but now we allow the enthalpy of mixing, delta HM, to be non-zero.
And to keep it simple, the model introduces a single interaction parameter, alpha or alpha. This makes the enthalpy of mixing a simple parabolic function, delta Hm, alpha XA XBD.
And this enthalpy term, this delta HMI, is exactly what we call the excess Gibbs free energy, GX dollar. It's the amount that the real free energy curve deviates from that ideal entropy-driven curve. And the sign of alpha, well, that determines everything.
Let's focus on the big one for material science, phase separation.
Phase separation can only happen when alpha is positive. That means mixing is endothermic. There's an energy penalty for A and B atoms to be neighbors. So for the solution to actually become unstable and split, that positive energy penalty has to be big enough to overpower the randomizing drive of entropy.
And there's an exact point where that happens, a critical condition.
There is.
Yeah.
Immiscibility starts to become possible when the curvature of the delta GM1 curve just hits zero right at the midpoint, at 50-50 composition. And the math for that works out to a very simple condition. Alpha has to be equal to 2RTR.
Which gives us the critical temperature, alpha 2R2.
Exactly. 2R is the absolute highest temperature where the solution could possibly separate into two phases. You can think of it like this. Alpha is the energy penalty for mixing, and $2 is the thermal energy you have available for randomization. If alpha is bigger than 2RTR, the penalty wins, and the system splits.
And above that critical temperature, there's just too much thermal energy. The system is always forced to be a single phase.
It is. But below Tegel, we get these two important boundaries that define what happens.
The binodal and the spinodal.
Right. First, you have the binodal curve, which you find with those common tangent points we talked about. Any solution with a composition between the binodal points is metastable. It wants to separate, but it needs a little energy nudge to get started.
And then inside that.
Inside that is the spinodal curve, defined by the points where the curvature of the delta GMU curve goes negative. Compositions between the spinodal points are absolutely unstable. The driving force to unmix is so strong that the solution will spontaneously decompose without any barrier at all. That's spinodal decomposition.
Wow. We have covered a huge amount of ground today. If you take away just three things from this, what should they be? I think the first has to be the physical reason for non-ideality. Henry's law deviations, your gamma value, they come directly from differences in bond energy.
Right. Atoms are either sticky or they're volatile. Second, you have to appreciate the power of the Gibbs-Duhem equation. It's your guarantee of consistency. It proves that if a dilute solute follows Henry, the solvent has to follow Raoult.
And third, the regular solution model. It's so elegant, it directly links that simple energy penalty parameter alpha to the critical temperature, to the Curie. That is how you can predict phase separation just from knowing the heat of mixing.
Absolutely. Those are the core ideas.
And just as a final thought, remember that these models are just the beginning. For something like polymers, which are huge molecules, you need models like the Flory-Huggins model. In those systems, that configurational entropy we talked about is much, much smaller because the long chains can't just arrange themselves randomly.
And when that powerful entropic drive to mix gets suppressed, you find that limited miscibility, phase separation becomes way more common, even at high temperatures. It really shows you that while energy determines the interactions, entropy often decides the final outcome.
A perfect thought to end on. Thank you for joining us for this deep dive into the behavior of solutions. We hope this really helped accelerate your learning.